One of the core principles in physics is that of the conservation of energy. Energy is what allows objects to move or change, like making a car drive forward. But energy doesn't run out. It doesn't just get used up or destroyed, because it can't. When you have an object or environment called a system, it is full of energy. But the only way that energy can enter or leave is either through physical matter, like a person walking into the car, or through the exchange of heat. There are different types of systems. Some allow both of these to happen, some allow only one or none. In an isolated system, it is impossible for heat or matter to enter or leave. Try to imagine an isolated system. I suppose the most obvious choice would be our universe. Our universe, that's infinite, is not surrounded by anything, as far as we know, so it's impossible for things to exit or enter. And because of this, there is no energy exchange, meaning that all the energy that's present in our universe is total and absolute and unchangeable. It is constant. It cannot be created or destroyed. Another way to look at this is through the lens of Noether's theorem. The exact math of this theorem is out of the scope for this video because it requires some calculus and it may be quite intense. But in essence, this theorem states that the laws of the universe are not changing through time. For example, our gravitational and electrical constants will stay constant. They are not going to change through time. Imagine, for example, a car driving up a hill. As it's driving up the hill, it has to fight the gravitational force. It requires a certain type of energy, let's call it energy 1, to move up this hill against this gravitational force. Imagine now that by the time you drive back down, gravity is suddenly stronger, and we have a larger gravitational force, F of G2. Then the energy, E2, that we gain from driving back down the hill will also be larger. But where did this difference go? Where did this new energy come from? Because we know that these changes are not possible, no new energy can be created this way, and no energy can be lost in this way either. If you're more interested in this, you can search up the invariance of physical law under displacement of time. That is, the fact that laws don't change with changes in time. Advances in general relativity now question Noether's theorem. In turn, this also questions the conservation of energy. However, this is much debated, and unless you are aiming for a career in general relativity, you can trust that energy is conserved. So it's true then that energy is not created or destroyed, but it's also true that we see a lot of different types of energy that seemingly come into existence suddenly and vanish just the same. For example, in a moving car we see the rotation of the wheels. We also hear the brumming of the engine and feel the heat of the pistons. These are all different types of energies. For example, we have kinetic energy here, the energy of motion, but we also have sound and heat. However, once the car stops, so do these. So, where did they go? The energy needed to create heat, sound, and motion is not produced by the car, but instead it is taken from the fuel, which contains chemical potential energy. It's not the car itself that creates energy, instead the car converts energy that it already has. It is called potential energy because it represents the energy something has the potential to release or transform into other forms. Potential energy is not always something you can see or hear directly. Instead, it's a stored capacity that explains how much energy an object could potentially use. The classic example is that of holding a ball above the ground. If you're holding this ball at this height, h1, we know that as soon as we let it go, the ball will fall all the way to the ground because it has a gravitational force acting on it. But while we are holding it, it's not moving at all. So in this state, it doesn't have any kinetic energy. It's not in motion, so it doesn't have the energy of motion, but it could definitely have it. In fact, as soon as we let go, it will start to move and it will gain kinetic energy. But the kinetic energy is not created from nowhere. It's not created by the ball or by the earth or by your hands. This energy already exists within the ball, and once you let go, it is only converted into kinetic energy. What do we call this energy that intrinsically exists within the ball based on its position? Well, this is the potential energy. And again, it's called potential because it gives the ball the potential to move. Now, if we look at our second ball, it's much closer to the ground, at height 2. It's still true that once we let go of this ball, it will also fall to the ground, but it's going to fall a much shorter distance, so it's going to need less kinetic energy because there's less distance to travel across. So this ball does have the potential for motion, but not as much motion as our previous ball. So it has less intrinsic energy, it has less potential energy than our original ball because it is closer to the ground and hence will travel less. Could you imagine a position of the ball where it has no potential energy? Well, since potential energy is the potential for motion or change due to an object's position, we can see that if the ball is located on the ground already, it's not going to fall anywhere. It has nowhere to fall, and it's not going to burrow through the ground. So it doesn't have the potential to fall. If you let it go, it's not going to move anywhere. So it doesn't have any potential energy. In this example, the potential energy of the balls is gravitational potential, because the motion would be exerted by the gravitational force. There are many different potential energies. For example, there's a potential energy between charges. Opposite charges have the desire to move closer to each other. So if you place them in this position, they have the potential for motion, which means that they have potential energy. And to be specific, they have electric potential energy. Similarly, chemicals experience chemical potential energy as they wish to interact with each other. This gives them the potential for movement and the potential to change. Hence, they have potential energy. So, potential energy is not always as obvious or visible as the real energy that we see through motion or heat or sound. However, it's absolutely necessary to ensure that the total amount of energy in the universe is conserved. It's more of a mathematical tool to predict the motion of objects or to predict how much they would like to move or change. Because if you can calculate the change in the potential energy, then you will also know the amount of energy that was converted into other forms. I'm going to introduce you to the formula for the total mechanical energy. The total energy an object has is its kinetic energy plus its potential energy, denoted by U. If there are no energy losses, such as through friction or wind resistance, then the mechanical energy will be constant. Any change in the kinetic energy is an equal and opposite change in the potential energy, and vice versa. You can picture it like a seesaw. If there is an increase in the kinetic energy, it is taken directly from the potential energy of the object. So the seesaw will tip sideways by the exact same amount. Conversely, when you experience a decrease in kinetic energy, the potential will increase in the same amount, which tips the seesaw in the other way. Another important concept is that of work. Work is the energy needed to move something across a certain distance at a certain force, which is given by F times d, where F represents the force in newtons and d the distance in meters. Like imagine pushing a box across the floor. You're pushing at a certain force, F, for a certain distance, d. If you're pushing at a greater force or across a longer distance, you're going to do more work on the box. Increasing both of these factors obviously requires more energy on your part. You will have to know the work-energy theorem, which states that work is equal to the change in kinetic energy. And this also makes sense conceptually, because before you do work, the box is sitting on the ground and it's not moving at all. Its kinetic energy is 0. But once you start to move it, it will start to pick up speed and motion, so its kinetic energy will now increase to some value. You're putting energy into the box through work, which is converted into kinetic energy. You're pushing the box, and that's allowing it to move. And so, when we go back to the equation for mechanical energy, any change in kinetic energy is given by work. And because any change in kinetic energy is an equal change in the potential energy is also given by work. Hence, work is the converter. Work allows potential energy to be turned into kinetic energy, or kinetic into potential. If you wish to change these values and tip the seesaw to the left or right, you're going to have to do some work. Either do work onto the system, which adds energy into the system, or work is done by the system. Imagine again that you have a box at this height above the ground. At this point, it has a certain potential energy, let's say that's x joules, and it has a kinetic energy of 0. Once it begins to fall, the potential energy is decreasing, whereas the kinetic energy is increasing, until it lands on the ground where the potential energy is 0 and the kinetic energy is now x joules. Do you remember what this principle is? This is the conservation of mechanical energy. However, this equation only holds up if the force is conservative. By definition, the force is conservative if it conserves energy, meaning that the total mechanical energy is always constant. But if you have non-conservative forces, like wind resistance, that's pressing up against the box as it's falling down, this is also taking energy from the box. Hence, this formula is no longer true, because energy is taken away from the box from an outside factor. If we ignore wind resistance and just let the box fall according to the gravitational force, it will automatically and spontaneously fall to the ground. That's because objects in space want to reduce their potential energy. That's also just because potential energy is the energy an object could expend if it obliges the forces acting on it. If there was no gravitational force pulling it down, then the box would not fall, and so there would be no motion, no kinetic energy, and no need for potential energy. So it's easy to understand that objects want to reduce their potential energy because the potential energy is just there because there's also a force that makes the object want to move or change. So in this example, the box will spontaneously travel down to reduce its potential energy. But if we look at this example again, we can see that the box is being dragged along the ground flatly. This means that the gravitational force at any point in this road is equal. When we push the box, it's not losing potential energy, so the potential energy is constant. But it's also clear that the kinetic energy has increased because the box is moving. But this is where the difference lies. The box is not moving spontaneously by itself, it is being forced by an outside factor. In this case, it's you who's doing work onto the box. You're adding your own energy, which adds to the energy of the box. In that case, the total energy of the box is increasing, because the potential is constant, but the kinetic rises. But in this spontaneous case, the energy is constant, and we say that it's the box who does the work onto its environment. That's the difference between having work done onto an object versus an object performing work onto its environment. In the case that work is done onto the box, it receives a positive value, because work is a measure of energy in joules and the total energy rises. When the box hits the ground, the box is performing work on its environment. The box is compressing the ground or having some other impact, which is written as negative work, because energy is now leaving the system. So just to recap, the mechanical energy of an object is only conserved if conservative forces are acting on it, like gravity. But in reality, the system is always impacted by external factors like friction or wind resistance. Objects are influenced by forces and wish to lower their potential energy, so if possible, they will move to an area of lower potential energy. When there are external factors that add or remove energy from our system, then they do work on the system. This can be positive when energy is added, or negative when energy is removed. In those cases, mechanical energy is not conserved because the total amount of energy is changing. In reality, the concepts of energy, potential energy, and work are all deeply intertwined, and there are multiple different ways to understand what energy even is. But in the end, it's deeply tied to motion. That's because energy itself is a measure of an object's change through motion. It's not important to memorize all of these different ways in which these concepts connect to each other, but having understood them even just once makes it easier to conceptualize these concepts in the future and draw different connections to different areas of physics. That's because work and energy determine how things behave, and in the end, physics is just a study of the behavior of objects in the universe.